Okay, good afternoon, everybody. My name is Chris. I am the president of the Association for Computing Machinery. We're pretty much the professional group for computer science, computer engineering. We have a lot of EEs and some mechanicals who are just really interested into computer programming. I'm not sure, I think most of you are freshmen, and I know CS majors don't have to take this class, or I didn't, so. But if anybody's really interested in computer science, it'd be great to see you come out. Let's see. Like I said, we are the Professional Computer Science and Engineering Club on campus. We have a lot of different people, neuroscience, biochemistry, people who are just really interested into computers. Sorry. Let's see. So throughout the semester, we do programming competitions. Usually the top prize is $300–400. So if you guys are interested in computer or programming, please come out. The last time our lower level programming, we only had 2 people, so they both won as long as they got one of the questions right. So we also do workshops. LaTeX is a pretty big one that we do. That's going to be for all engineers because you use LaTeX in a lot of different things. We do also more programming-based workshops. We do events. We have a barbecue coming up, so that's cool. We're going to actually do a trip to Silicon Valley. We're going to go to Lockheed Martin, hopefully. That's still a big if, so if that sounds interesting to you, come in to our meetings, and then we do a lot of different fundraisers. So how you can find us, we have club meetings about every other Monday. We have one next Monday at 5:30, and it's in the Lily Brandt Reading Room in the De La Mare Library, you know, the building with the really, really tall doors. We also have a Facebook page. Just search for UNR ACM, and then you can ask any of your professors, not just your CS, CPE courses, but anybody. You should be able to figure out how to get a hold of me. Also, my email address is christopher.ginac, GINAC, or you can just email acm@cse.unr.edu. So I think that's it for me. Yeah.
All right. All right, so we've got a big week ahead of us. First off, you guys can celebrate. There's no class on Wednesday. Okay? Yeah. It's the best announcement I have for you all day. Checkpoint 1. Nice. Someone's really excited about that. Big plans for Wednesday. All right, checkpoint 1 is in the EDL on Thursday and Friday. All day. You have from 10 till 7. If you show up at 7:05, the doors are locked. You can't come in. So please make sure that you get in there, and I would suggest coming in early. I know some people are like, well, you're telling everyone to come in early. That means the line's going to be really long Thursday morning. I can guarantee you that is not the case. I'll tell you to do that, and no one will listen to me. So please, if you want to get through quickly, come early if you can. That is the best way to get through this checkpoint. You'll meet with the TAs, you'll meet with Dr. Lacombe and with me, and we will go through your checkpoint. Make sure when you come to your checkpoint that you have printed out the grade sheet and completed the parts that basically don't involve us giving you points. If you go back to the lecture I gave, I believe 2 weeks ago, it shows you the checkpoint pages, and there's big squares in red around the things that you need to have done. So make sure you come to the checkpoint prepared. That will make things go a lot faster for you also. Please, too, make sure that you look at the grade sheet and see what's all required of you so you have all the information you need. The best way to get a good grade in this class is to know what's expected of you. And so we put that out there for you. Please go ahead and read that. That helps a lot. Any questions on checkpoint? Okay. All right. Next up, you need to view the fuel cell and battery learning module and take the quiz by Monday. It's actually available today. Sorry. Yes. He asked if there's somewhere in the textbook that lists the exact weight of the fuel cell and the NXT. I do not believe so, but there is a scale in the EDL, so when you come in or go by there and ask one of the TAs that are there, and they'll weigh it for you or help you weigh it. Yes? He pointed out week 3, Monday lecture, there's a table with estimates. I'm just not sure that they're exact. But you can use those for now, but you might want to go by and weigh your stuff. Okay, anybody else? Okay, so what else? CATME surveys. I'm sending those out again tonight for your third one. Again, please be open and honest with those in your comments. That helps a lot. If you come to me later and say you're having a problem, I like to look at CATME and see what's going on. So please make sure that you are filling those out. Okay, they're due, again, a week from today at 11:59. On that note, when things are due on the computer by 11:59, at 11:59 you get shut out. And so you're trying to upload and it won't let you. Don't run into that problem. Just start a little bit earlier than 11:55 and you should be okay. Your graded design concept reports are going to be placed in your mailbox in the EDL as soon as the grader can. That is a huge, huge time-consuming task for the graders. So it may take them a little time, but they should be in your box soon. And then grade forecasts are now available in Web Campus. So we've put in a column in Web Campus. It's got your grade up to date for everything that you've turned in. So please be aware of your grade, take a look at it once in a while, check in, make sure things are up to date. If you think that you are having problems with some sort of grading issue, okay, the first thing you do is probably talk to your Skills Lab TA since they do most of the grading. Okay? Unless it's CATME or Clickers, they take care of the grading. So you want to email them. You can also copy Dr. Lacombe and I on there or email us and it'll get shuffled around. But don't wait until December 1st to start arguing about grades. It's easier to do it as they go. So if you're having problems, please let us know. Okay. Also, bring your safety goggles to Skills Lab. We will issue your fuel cell if your team rented a kit this week. But make sure to bring your safety goggles. You can't work in the lab anymore without safety goggles. And make sure that you've taken that safety test and passed it if you haven't. Okay. All right. So checkpoint 1, Thursday or Friday, again, you have from 10 a.m. till 7 p.m. It's your calculations and your part list. It's worth 25 points. Web Campus has the description and the grading criteria. I cannot stress to you enough to look at the grading criteria and make sure that you've brought everything that we expect of you. That's the number one easiest way to get points in this class is to bring what's expected. Okay. Again, 10 to 7, please come early. Only one team member can be absent, so that might limit your times. That means that make sure your checkpoint is done early, so if you guys have a window of opportunity, you guys can come down. If one person only has an hour free on Thursday and Friday, you might want to send everyone else to get in line or something like that so that they can be there. The later you come, the longer the wait. There was times last year when we were here till 10 p.m. So I'm telling you, come early. The mornings are quiet. The evenings are busy. All right, structured programming part 1. We're going to go through some basics of programming today. Okay? It's mostly just information background. We're not going to actually talk about how to program, but we're going to talk about why we program. We're going to talk about what is a program, having states, and taking steps to change them, and then responding to and changing states. Okay? So these are the 4 things I'm going to cover today, and then I'll pick up with the rest of it a week from today. So why program? Suppose that you have graduated from UNR and you have your first very exciting engineering job, and you're asked to do the following. You need to create a scalable chemical process to synthesize large quantities of a product. How are you going to do that? Or they say, manage a project in the team to create a new lightweight aircraft. And you'll say, oh, I made a lightweight hovercraft. I'm good to go. Or upgrade an interstate highway with new lanes while managing present traffic operations. As they're all familiar with the I-80 construction. Or develop a system that controls and applies a new form of low-emission X-ray. So the point being is that you could be asked to do some major projects when you graduate. So what would you do? Very likely you're going to create a well-organized, highly structured, and carefully specified series of steps that would accomplish the given task. You're probably going to start with a Gantt chart and look at what do I need to accomplish, and you're going to break it down. It's kind of like when you're writing a paper and you put in an outline and you say, okay, these are the various things that need to happen. And then you look at the time structure. Okay? That's developing a program. Okay? So a program is basically a well-organized, highly structured, and carefully specified series of steps. So a series of, according to, I think, Wikipedia, a program is a series of tasks or steps applied in a specified sequence that will accomplish a stated goal. So you are trying to get this new x-ray machine or reconstruct I-80 or whatever it is, and you have a series of tasks to get there. Okay. Program examples, your degree program is a program, right? When you come to UNR and you say, I want to be an engineer, and they say, what type? And you say mechanical. And they say, here you go. And they give you a flow chart and they give you a list of all the classes or a program of study. Those are tasks that you need to complete in order to graduate, which is your goal, hopefully. Okay. A program that causes a hovercraft to move over a specified course. You guys will be writing a program. You have to program those NXTs so your hovercraft can get to the end of the course and back. Okay. So it is any process or procedure whose consistent, systematic, and correct or appropriate steps are necessary to manage a large, complex system. Okay? So it's steps that you put together to manage a system of some sort. And this can apply to a lot of things. You'll see on this next question. Quick clicker question number 1. Are you guys set up? I kind of skipped over that. Channel 65. I am on the right number, I think. Oh, thank you. You guys are on it today. This does not look right. Yeah, give me a second. Let's try it. Sorry, guys. Session 924. All right. Well, you guys are off on the clickers today because my clicker is for 924. So, 2 weeks in a row. You guys are here for free today. Sorry. Okay. So, let's have a raise of hands. This will be very official today. I'll remember every face and take roll later. Is the process, laws, etc., by which the U.S. government works a program according to our definition? You guys are just going to leave, you lazies. All right, we'll have a pop quiz later. Option 1, no. Or option 2, yes. Yes, good, thank you. You guys are smart. All right. Government has a lot of features of a program, or at least it tries to. Okay? How well it succeeds and how often it deviates from these is a matter of debate. But this is not poli-sci or government, so we're not going to discuss how it works. But yes, the government is a program. The government has tasks and steps applied in a specific sequence, okay, to accomplish a stated goal. All right. So moving forward, I'm going to give a secret password for later. People who left don't get it. Make them feel bad as they leave. Okay. In a program, a state is a status or condition of one or more part of the system, right? So sometimes we say, man, I'm in a state today. I'm having all sorts of computer issues. State examples could be, your car is in the garage. Your car engine is running. The car's brakes are on. The car's radio is off. These are all different states. Okay? States are just something that's happening at that moment. Any of these states can change independently or together. My brakes can be on and my radio can be off at the same time. It doesn't matter. And I can turn my radio on and apply my brakes at the same time. Okay? So any of these can happen independently or together, each being a unique piece of information that can tell us what is going on in a particular system. So again, state examples are just the state of your car at this time, or the state of your hovercraft. Is it hovering? Is it going forward? Is it returning back? All those different things. All right. So having states and taking steps, a set of specific steps is necessary to conduct an action, and the result is called an algorithm. Okay? An algorithm is a set of steps. So the program you write, implement, and use are all based on algorithms. And you guys are going to be writing programs in this class in order to control your hovercraft. In your hovercraft programs, the algorithms used will only require a specific series of steps. It will also require that components are in specific states. If you turn on your propulsion fans, but you don't have your lift fans on, you can't go anywhere. Right? So it's got to be in a specific sequence. Driving a car is a good example. Okay? You can't leave the garage without turning on your car. Right? So think about, we're going to talk about how to make decisions, and it's based on the state that you're in. Okay? All right, so my second question for you guys to raise your hand to answer is, an algorithm might best be described as which of the following? A cookbook recipe, a moving vehicle, a large structure, a TV screen, or a clear desktop? What do you got? One? Good. One, a cookbook. Okay. When you want to bake something, typically you follow a recipe very carefully, or it doesn't turn out very well. Algorithms are something we will talk about a lot in class, and it's on your final exam, so good thing you're here. All right, the order of steps is critical. So a sequence example is get in the car, check, turn on the engine, start driving, find a parking spot, park and turn off your car and get out of the car. That might be how you get to school, right? You can't park and turn off your car until you turn it on and drive forward. There are specific sequences that you'll need to follow in order to program your hovercraft. If you got out of the car before stopping, the algorithm would not work. So algorithms are time dependent. They're sequence dependent. It matters the order of your steps. In a chemical procedure, some quantities must be at a certain temperature or pH or something before they can move on to the next step. Okay? While building a highway, we have certain layers of material. Okay? You need certain base materials. They need to be compacted before you can move on to the next layer and add it. Okay? You guys can think of numerous examples where the sequence matters. Okay? For you guys that are into computer programming, certain data must be stored in memory before you can move on and use it. Same is going to happen as we program our hovercrafts. So algorithms apply outside of computing, so you know. So this isn't just for computer majors. All right, in the case of the hovercraft, again, as I said, the lifting fans must be in the on state. So when those fans are on, that means you lift up. And then the propulsion fans can be used. We could turn on the propulsion fans first, or however you're going to propel your hovercraft, but nothing's going to happen because you're not up off the ground. You've got too much friction. Right? So the time matters on this one. All right. So here's a really basic hovercraft program. You see at the start of the program, the state of your lift relay is on, okay? And the state of your propulsion relay is on. And so when you're on, that means that trap door is open, so your electrons can't flow through your circuit. And so what this means is that you're waiting at the start line, just there. The next step is close lift fan relay. Well, if we close the relay, okay, that means the energy is getting to our lift fan, so now we're up off the ground. And then I close the propulsion relay, step 3, and now I'm going forward. Okay. And then when I get to the end here, I can close my propulsion close my lift and then keep my propulsion open. And I'm going to be hovering in one place at the end, or vice versa, excuse me. Okay. And then I can open my lift fan relay and stop. And then I end my program. So this is super simple. You guys need to start thinking in these terms, these sequence terms, about what you want your hovercraft to do. Make sure that your design is something you can implement. And the easiest way to think about your computer programs before you get to learn the computer software LabVIEW we're going to use is to start thinking about things sequentially and write down the exact steps that you expect your hovercraft to go through. And once you have those steps written down, or an algorithm of sorts, then we can program. Okay? Remember, your relays are like switches. So if the trap door is open, no electrons can flow. You throw the switch or throw the relay, it's called. The door closes, electrons flow. Okay? So the main thing here is taking a step is commonly going to change the state. So if I open or close a relay, then I'm changing the state of my hovercraft. All of a sudden I'm lifting, or I'm going forward or stopping, or whatever it is, but I am changing the state. And that's the main thing here. Next. Okay. So a more sophisticated program is I just added in an extra step. I said maintain all states for 2 seconds. So now I'm hovering in place, but I'm going to hover for 2 seconds so I can make sure I'm balanced, and ready to go. Set, I have my positioning right. And otherwise, this is staying the same. Again, I've got down here, when I go forward for 1 second, I maintain, or for 10 seconds now, I think that I need to go forward for 10 seconds, so that's my extra step. You can add in all the steps you want, and they'll get more complicated than this. But just think that you are changing the state of your hovercraft. Okay? So you're using your algorithm to change the state. So again, I highly suggest you guys write an algorithm for your hovercraft. Start thinking about what you want it to do. What is the motor going to do? What are the fans going to do? If it sees black or white, what do you want to change? Those are things you can start thinking about. All right, in the previous example, running a propulsion fan without the lifting fan would not be helpful, right? Because our hovercraft's not off the ground. So if I turn on my propulsion fans, it's not bad. Or my propulsion, whatever you're doing with your fuel cell, but it's not going to work. So using the propulsion fan depends on the state of the lifting fan. If the lifting fan is off, I get no propulsion. If the lifting fan is on, I get propulsion. So we can think about this as a simple if-then conditional situation called decision-making or selection. If my lift fan is on, okay, then turn on my propulsion fan. That's an if-then statement. So here you have a decision-making tree thing we call branching. Okay? One way to understand the decision-making process is to view it as a flow chart. You guys have all heard of flow charts. Okay? First thing you do is you come in and I'm saying, is sensor 1 white? Well, let's go with yes. I feel like going higher here. So yeah, it's white. Oopsies, sorry. So if it's on white, okay, then I check sensor 2. If that one's also on white, then I want to go straight, because that means I'm on the beginning of the board, I'm out of the black, I just need to go straight. Later, I'm just going to keep running this program over and over. I check sensor 1, and it's on white, and then I check sensor 2. But sensor 2 all of a sudden is not on white. It's hit the black line, or the end of the course. And so I might need to turn, because if one sensor hit black and the other one didn't, that means that I'm curved one direction or the other, and I'm meant to be going straight. So I'm going to make a left turn. Same thing coming down here. We can check sensor 1 and then say that it's on black, and we check the other one and it's on white. So that means I'm turned maybe the other way, so I want to go to the right. Or my last condition here is that all sensors are on black, and so then I need to decide what I want to do. It's up to you. For you guys, if you get to the end and both sensors are on black, you got to figure out how you're going to turn around and come back. But you are checking the state of your system, okay, and making decisions. All right. So, many systems, including your hovercraft, are programmed to respond to changes in states, as we've been talking about. Okay? And so the way we do that is we receive input. You guys have sensors on your hovercraft. Light sensors at the least. We talked about, I think last week, you could put on a third sensor if you wanted. Maybe you want to use a distance sensor or a touch sensor or something like that. Okay? But those sensors are there to check the state. Okay? Like we have feelings that make us feel things or put us in a state. Okay? These sensors are telling us where we are. So inputs such as light sensors are used to make decisions based on the inputs and then change the state by controlling the outputs. You guys have complete control of your hovercraft. The sensors tell you, hopefully, help you indicate where you are, and then you're going to use your motors and your fans and your fuel cell to change the state. You want to go forward, you want to stop, you want to turn around, you want to come back. Okay? So they're all working together to make decisions. All right, so here's a much more sophisticated program. You start your program, okay, so both relays are open, so nothing's going on there, and you're waiting at the start line. And then you close the lift fan relay, which means that you are hovering in place. Then it says maintain all states for 2 seconds. So no changing your relays, you're just staying there, you're hovering. Both sensors are on dark, okay, still. That's our third thing here to make it complicated. So we've got sensors now in this. Then we close the propulsion fan relay. Okay, and so we started moving, and now both my sensors are reading light because I've moved out of that black zone at the front. After that, I maintain all states. I want to go forward. I'm waiting to get to the end of my course. Okay? And then I'm taking light sensor data because I want to know when I get close to the end because I can't hit that back wall or I fail. All right. So what I can do is I can say, here, go back to this if-else statement we talked about a couple slides ago and say if light, then go back to step 4. And if dark, this should say proceed to the next step. So you make a decision. I know, it's bad today. But you have that if-else statement. That will help you guys. And so if you think back to the flow chart we went through where we said, well, if 2 sensors are on white, I probably want to go forward. If 1 sensor is on black, I want to turn to the left. If the other one's on black, I'll turn to the right. That sort of thing. Okay? Start mapping this out for yourself and what you guys want to do. All right. So in the example shown, we run through the system once where I'm saying, okay, I want my hovercraft to go to the end, but I'm really only left room to check my sensors once. And if I only check my sensors once, how do I know where I am at that exact moment where I check the sensors? I don't know, right? It could be anywhere. And since we can't just set up our hovercrafts to go forward for 5 seconds and come back, that's cheating, then it's nice to have what we call loops. Okay? And a loop means that your program will be repeated infinite amount of times, or as many times as you want it to. So if you loop through, then that means you can check your sensors multiple times. And if you're checking your sensors multiple times, then you know where you are, hopefully. Or that is the point anyways. Okay? So we take sensor input, and we're using that input to affect our state. We change our state based on what the sensors are telling us. Once we change our state, you know, our outputs have worked. We use our outputs to change our state. Okay? So we're comparing data. We're looking at where the light sensor was and where it is now, comparing data to change our state. All right, any questions about data comparison? No. That's it? You guys are easy today. I am actually finished for the day. So thank you for staying, you guys, and with my lack of clickers. Please make sure you are ready for the checkpoint. Take this 20 minutes, meet with your team. I know there's some people that I have appointments with. We can just talk in here. So have a great day.